In this video, we'll be showing that if T is a linear transformation that goes from a vector space V to a vector space W, and that this transformation is linear, then its inverse, in other words, T inverse, will also be linear. So let's just do a recall. Recall that for T to be linear, for any transform to be linear, it must follow two conditions. So if I say T is whatever linear transformation, and I say T maps V1 plus V2, then this needs to be equal to T V1 plus T V2, right? So this is for all V1, V2 belong to V. And then, so that's my first condition. Then my second condition is that T CV1, where C is a scalar, so it belongs to R, T CV1 is equal to C times T V1 for all V1 belongs to V. So this is how you determine if something is linear or not, right? Okay, so now I want to show that T inverse is linear, and what's important here is that we're given that T is a linear transformation. Okay, so let's start the proof by saying, so let's take we're going to take two arbitrary elements of W, which is the domain. So take W1, W2 belong to the domain, sorry, not the domain. I said domain before, I meant the codomain. W is the codomain. So we have W1 and W2 belong to the codomain. So that means if you take the inverse of W1 plus W2. So notice here that I'm not starting with V1 plus V2 because it wouldn't make sense to take the inverse of two elements in the domain because they're not mapped yet. I'm taking the inverse of two images, right? Because the inverse of something gives you what it was mapped to, right? So that's why I'm taking W1 plus W2. And so I know, so from here, I know that W1 is actually equal to T V1, right? Because if you picture this sort of in terms of vector spaces, so let me create two vector spaces. This is T, it's mapping V to W. So I have W1 and W2 here, and I have V1 and V2 here. So now I'm saying that V1 maps to W1. This is just, well, this is what I'm saying here, right? And now I'm also going to say that W2 is equal to T V2. In other words, V2 is mapping to W2, right? So now I know these two things, right? So remember that W2, V2, W1, and V1 are all arbitrary, right? It's just I know that W1, W2 is in big W, and I know that V1, V2 is in big V, right? Okay, so now because I know these two things, right, then I can rewrite this as T inverse of TV1 plus TV2. Okay, but I know that T is linear, right? So T is linear, right? And remember what that means from here. From here, if T is linear, then T V1 plus V2 is equal to TV1 plus TV2, right? So what do we have here? Here we have the result. So we can actually write that backwards and write T inverse T V1 plus V2. And I know that if I take the inverse of the inverse, so if I have an inverse function and I take the inverse function of that function, then I'll just get the identity map. In other words, I won't get anything. So that's an important note. So if I take T inverse of T, then this just gives the identity map. So in other words, it doesn't do anything to V. So if I take T inverse of T of V, it'll just give me V, because I'm not doing anything, because it's like I'm applying the mapping and then I'm canceling it with the inverse, right? So the same thing can be said here. I just get V1 plus V2. Okay, but V1 plus V2 are elements in the domain, right? They're here. And I know that if I take T of V1, then I'll get W1, right? So here, if I take T of V1, then I'll get W1. But if I take the inverse on both sides, so I do T inverse TV1 is equal to T inverse W1. So I'm not doing anything, I'm just taking the inverse on both sides. Then this here will sort of quote unquote cancel. So I get V1 is equal to T inverse of W1. And similarly for V2, I'll get T inverse W2. So then what I get from this is I'll get T inverse W1 plus T inverse W2. But what did I start with? I started with T inverse of W1 plus W2, and I'm left with T inverse W1 plus W2. So I've shown the first part of my proof that T inverse of W1 plus W2 is equal to T inverse of W1 plus T inverse of W2. Right, so that's the first part of my proof, right? It's just showing that if you take the addition of two elements and you apply the mapping, then it's just the mapping added together, right? Okay, and then the second part of my proof, right? So what I want to show, so my goal here is that I want to show that T inverse of CW1 is equal to C times T inverse of W1. So where I have C belongs to R, so C is a scalar, and W1 is just some element in W, right? So that's all I know, and I want to show that this will lead to that. So the same sort of concept that I used in 1 applies to 2. So I'll start with the left-hand side. Right, so with the left-hand side, I have T inverse of CW1, right? And I know from before that I can write W1 as TV1 is equal to W1, right? That's just the mapping that I showed over here. It's just this thing, right? So I can do the same thing here, and I can substitute or take what V1 really is. That is, it's the linear transformation of V1. I can rewrite this as T inverse of C T V1, right? And now, because T is linear, right? Because T is linear, I know that, sorry about that. I know that CTV1 is actually equal to TCV1, right? So I have this side, and I'll just replace it with this side. So what I get is T inverse of TCV1. And I can say the same thing here, that I'm taking the inverse of the so I'm applying the inverse transform to the actual transformer. In other words, I'm not doing anything. So just this sort of, this cancels. Of course, a transform can actually cancel, but it's sort of, you can sort of picture it that way. And so this is equal to CV1. But the same thing can be said here that I said right over here. So I can actually write V1 as T inverse W1 because V1 is a mapping from because T takes V1 and brings it to W1. So if I take the inverse of W1, then I'll just get V1, right? So CV1, so this is because, so I'll go over this again, because TV1 is equal to W1, then I can just take the inverse on both sides. So I do inverse on both sides, and then this again does nothing, so I'll get V1 is equal to T inverse W1, and then this will give me C times T inverse W1. So notice that I started with this T inverse C W1, and my result is C times T inverse W1. So I've shown that T inverse C W1 is equal to C times T inverse W1. So because I've shown 1 and 2, I can say that T inverse is linear, right? So I showed, first of all, that if I take the inverse of two elements, then I'll get the sum of the inverse of those elements. And then if I take the inverse of the scalar multiplication of two elements, then I'll get the scalar times, or the scalar multiplying the inverse. And that shows that T is linear.